Hello, my two-lab sequence is on equivalent circuits. The data represented here is data that students would have collected during the inductive part of the lab. So they basically made all of the measurements in the lab prior to the second lesson, where the data will be analyzed to allow students to infer equivalent circuit relationships. So basically I had them collect data on different connections of batteries and resistors in circuits. There's connections for series, parallel, for both batteries and resistors. And then there's a combination circuit where it includes batteries and resistors connected in both parallel and series configurations. So in this tab, you have the data for students connecting 4 different resistors in series of 4 different values. So there's a total of 16 resistors. So they took the measured resistance using a multimeter of 1 k ohm resistor. Then they added another k ohm resistor in series, and another k ohm resistor in series, and another k ohm resistor in series. And they measured the total resistance as they kept adding a resistor in series. And they repeated the process for 2 k ohms, 3 k ohms, and 4 k ohms, and then plotted the results. So what I would want students to infer from this graph is that the relationships are linear. The slopes of the lines end up being equivalent to the value of the resistor being added, and that there are 4 separate lines that indicate that there's no relationship between the value of the resistors and the equivalency of connecting resistors in series. So from this graph, they should be able to infer that connecting resistors in series is the equivalent resistance is just equal to the sum of the resistors that are being connected. In tab 2, we went through the same exercise, except now we were connecting resistors in parallel. And from the graph of the results, students can see that it's an inverse relationship since the slope of the lines are going down. And they can also see that it's not a linear relationship. This is probably too much for the students to figure out, and we'll end up having to give them the actual result. But if they were able to infer just those 2 relationships here, I'd be more than happy. But the equivalent resistance relationship here is 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and continuing on forever. Then we went through the same process with batteries, connecting 4 batteries in series of 4 different values and plotting the results. And again, they got the same types of results as they saw for resistors, and I would expect students to infer here that the equivalent voltage of connecting batteries in series is just the sum of the batteries that you have connected in series. Here we went through the same exercise again, except this time we were connecting the batteries in parallel and plotting the results. So as you can see here, you have flat lines, so I would expect students to be able to infer that connecting batteries in parallel doesn't change the voltage. So a good question here is, based on their life experiences, what would be a good reason for connecting batteries in parallel, since it doesn't actually change the voltage in the circuit? And the obvious thing to kind of guide them to is the size of batteries in compact cars versus large full-size cars or trucks. That you know, the cranking amps when you start the car needs to be much higher for the larger cars. So that allows the students to infer that it's just to be able to supply more current. And lastly, we have a combination circuit that the students measure all of the circuit parameters for using a multimeter. In the follow-on lesson, once they've actually inferred all of the equivalent circuit relationships, they'll calculate all of the circuit parameters using the equivalent circuit relationships and Ohm's law, and then they'll compare their calculated results to the measured results that they obtained here during the lab.